Number 6, a new social media site is increasing its user base by approximately 3% each month. If the site currently has 22,590 users, what will the approximate user base be in 10 months from now? So this is 3% per month, and that is talked about in terms of months. So this means that this guy's going to be a consistent per month increase. Okay, so here is our initial value. We're going to go up 3%. Okay, don't forget the 1, or else your answer won't even make any sense. Okay, and we want to set that to 10. Okay, so really this is just I don't even know if I really need to plug this in for you guys. Maybe I should have these answers ready. Let me do it quick here. Should have 30,359. And make sure you label it users. Okay, that's important. But notice that I trimmed off the decimal because 0.07 users doesn't make any sense. All right, a rubber bouncy ball is dropped from a height of 176 centimeters onto a hard, flat floor. And after each bounce, the ball returns to a height that is 16% less than the previous maximum height. All right, so that's interesting. We start off at a certain height, and I'm not even going to bother putting the decimals. He's going to decrease by 16%, which means if 1 minus 0.16 is 0.84, so this means every time the ball bounces, he's 84% of what he used to be, because he loses 16%. Okay, so how tall is it going to be on the 8th bounce? Okay, I imagine not much, but let's see. Now this is in centimeters, so remember that you're carrying that with you. I'm going to put minus 0.16, or you could have just put 0.84 as long as the number is smaller than 1. That's how you know you're doing it right. 8 bounces, and it looks like it's at 43. Now here we can actually use the decimals. In fact, they did do 2 decimal places, and it does not say which one. So if it's going back 2 decimal places there, I think these are called significant digits in chemistry. You're going to go 2 significant digits here. Okay. Now notice then, again, we're not doing a lot of math. It's all in the setup. It's recognizing what the situation is and then using the exponential models. For we got compounded. Yeah, okay. Car rental company assumes each car in the fleet depreciates by 6% per year. If the initial value is $30,000, what will be in 11 years old? In 11 years, it does say per year, and they're asking for 11 years, so we're good. All right, amount. We start off with 30 G's. We're going to depreciate, so that word should trigger a minus 0.06, and we are asking what is it going to be in 11 years. Now I'm surprised if it's a car that it would depreciate by 6%. It's usually more than that. Okay, 1 minus 0.06, and then to the 11th power, and it'll be worth a little over half of what it used to be. I think cars depreciate a lot more than that, and because we're dealing with money, and they did go 2 decimal places, we're going to go 2 decimal places there. So we got 0.95. Okay. All right, and that is in money. All right, number 9. Savings account balance is compounded continuously. Okay, that is his own formula. Okay. Okay, good. All right, so compounded continuously. That is the PERT formula. So amount equals the principal times e to the RT. Did you set your timer, Atticus? Okay. All right, so our initial 4 more. All right. So we're going to start off with 1937, 0 change. We're going to multiply to e to the r times t. Now the r is the percentage. Okay, now if this was continuously decays, then we would put negative 0.04. But that's not what this is. The balance is going to go up. Okay, so we're going to go by 4%, and we want to know 7 years. Okay, so we're going to multiply that by 7. Now, e to the x is his own special button. All right, so 19 0.37 times e to the x, which is this button right here, is the ln right there, e to the x. What it does is it gives us the e, but then it also just gives us the exponent immediately, so we can type it in exactly as we see it. And that makes sense. We've got $2,564.23. Number 10, for a period of time, an island's population grows exponentially. Okay, if the population doubles every 17 years, and the current population is 1,127, what will the population be seven years from now? Okay, so if it doubles every 17 years, that means that in 7 years it did not have enough time to double. So our answer should not be this doubled. Okay, it's going to be 7 is less than 17. So we don't expect our answer to be doubled. It will be higher, obviously, but not doubled. Okay, now how do we handle this every 17 years it doubles? All right, well, this is basically kind of a doubling, tripling, or a half-life problem. And so this guy looks like our initial amount, but then we have the doubling, okay, and then we have t divided by the h, okay. Now the h is what we call the half-life, all right. In this case, it's the doubling life, okay. Now the reason I put the 2 is I'm actually going to rewrite this. Imagine if it was the same process, but you're going up, but you're going up by 100%. Okay, that's basically doubling, so that's why I put the 2 there, okay. So even if you forget this as doubling, I don't know how you can, but if you did, then you could just kind of think about how this works, okay? Now, when we raise it to the power, though, we're not going to be raising it to 17. We're going to be raising it to 7. But what does that mean? It means then that doubles, now they're playing tabs. Okay, now in 7 years, though, I want this to double if t would have been 17. Then I would have just raised it to the first power, but I'm not doing that. I'm raising it to some fraction of 17. Okay? So I want to know, if I were to take 7 divided by 17, I'm not raising it to a full double time. I'm raising it to 41% of that double time. So I can't take 100% of a doubling. Okay? That makes sense. If it was 17, it would be a perfect 1, and then it would be 2 to the first power. It would have doubled. All right, so now with this setup, I'm going to go ahead and type in exactly as I see it. Okay, 2. And then I'm actually going to go ahead and put in a fraction here. Don't know why I did that. There we go. All right, it'll be 7 over 17. And there we go. So 1,499. And this is a population. So 1,499 people. Okay. All right, because we're just going to round down. All right, now does this make sense? It should, because I'm not even going half of the doubling time. Okay. All right. Now here's a true half-time problem. A half-life problem. Radioactive isotope molybdenum 93, which is an isotope, decays exponentially. If the half-life is 5,000 years and the current mass is that many grams, what will the mass be 5,000 years from now? Now this is interesting, okay, because we got the amount, we don't know, but we do know that we started off with 658.10 grams. Okay, I didn't have to put the G there for grams, but I am going to do the half-life thing. Okay, so I'll put a half. I want to put 0.5, it's up to you. 0.5, it's up to you. But here is the half-life thing that we were working on here. If I have a half-life of 5,000, and I wonder what it's going to be like in 5,000, well, then what I'm saying is it's basically 5,000 over 5,000. That's exactly the half-time, okay? That is when I take it, exactly half of it would have decayed, okay? So 658 times this, and then times, you know what, we're just going to cut it in half. So I'll just go 0.5 raised to the first power is the same as 658.1 divided by 2. Okay, it's the same number. So this we will put the decimals because we are talking about grams. All right, and that is our final answer.